Welcome back to the Water Resources class. I'm going to continue with a module on floods and soils. I'm going to start out here by suggesting that you take some time and go back to the previous module and look at stream hydrographs. Make sure you know those basic elements and how we express hydrographic elements such as flow and stage. You may remember the diagram in this figure from one of the tests or quizzes. Make sure that you know all of those. The PowerPoint for this lecture, which will be posted to Blackboard, does include an additional slide after this one that has the answers on it for your ease in reviewing. And also make sure that you can answer these questions that are listed on the left. That's a good indicator to you that you're prepared to move forward with this lecture. You also should review the land use effects on hydrographs. The figure on the right here has shown up in any number of lectures so far this semester, which is probably a clue that it's a really important idea and concept that's embedded in that figure. And make sure that similarly you can answer the questions that are listed here on the left part of the slide. And when you answer these questions, make sure that you're thinking in terms of the watershed factors that we covered way back at the beginning of the semester in an earlier module. I told you at the time that those watershed factors are really important and we'd keep coming back to them all semester. So this would be a good time to go back and review. Okay. Now before you go any further, it might be a good idea to go ahead and pause, pull up this PowerPoint from Blackboard, and review those concepts. Once you're done with that, I suggest you continue the lecture. All right, we'll pick this up then. The first concept that we're going to introduce in this module is the idea of a recurrence interval. A recurrence interval is a statistically based estimate of the probability that a flow of a given magnitude will occur within a given time period. The time period we're talking about is usually annual. That avoids what we call autocorrelation. Sometimes a flood may occur and that flood may have a really long receding limb. So we may get a flood peak in the middle of August, say, but it may take till the end of September for flow in the stream, especially if it's a very large watershed, to get back down to sort of the normal base flow. So by looking at annual peak or maximum discharges and using those annual peak discharges, which in other words is the biggest discharge in any given year, by using those to calculate recurrence intervals, we avoid this autocorrelation because in the scenario I gave you where the flood starts in August but it hasn't finished until September, September is high because it's correlated to an event that occurred in August. So we usually look at these things annually. That's the bottom line. Recurrence intervals are probably best expressed as probabilities, such as a 1% probability flood. A 1% probability flood would be a 1 in 100 probability, which would be what we often call a 1 in 100 year flood. We'll talk more about that nomenclature in a second. We'll come back to that. So let's look at recurrence intervals in a tabular format. On the left here we have the recurrence interval in years, so a 500-year recurrence interval will correlate to a 1 in 500 probability or a 0.02% chance of occurrence in any given year. And that last column is really important. The popular lingo is to say a 500-year flood, and that really is a misleading thing, especially for the general public. It sort of leads people to assume that, well, we had a 500-year flood last year, we're good for 499 more years, right? But that's not true. A 500-year flood is just the flood that has a 0.02% probability of occurring in any given year. You could have 3 500-year floods in 5 years. That's an exceedingly low probability that it will occur 3 and 5 years, but in any given year, there's a 0.02% probability. Similarly, a 1 in 100 year flood is simply a 1% probability in any given year. An important assumption in estimating recurrence intervals, or RIs, is that the watershed factors are constant. Now think about this for a second. Can we really assume that all our watershed factors are constant? Well, if climate or land use or any of the other watershed factors change, then the previous hydrologic responses within the watershed will no longer be representative or predictive. In other words, we have maybe 100 years of record in a watershed. If nothing's changed, if the climate hasn't changed, the land use, the vegetation, the slopes, the topography, the geology, all those watershed factors, if they've remained exactly the same through that 100 years, then that 100 years of data probably includes a wide range of precipitation amounts, both daily and longer term precipitation. We've probably had a lot of wet periods in there, a lot of dry periods. And so any point in that data set is probably representative of how the watershed would respond to the same event in the future. So if we had a week of rain where we got 2 inches of rain every day 50 years ago, if nothing's changed, the watershed's probably going to respond similarly to that same rain event now as it did 50 years ago. However, if the climate's different, meaning that the amount of rainfall and the timing and all of that has changed, then that assumption is no longer good. I would encourage you to review this idea. It's called stationarity. It's something that we've talked about earlier in the semester. One of the papers you were assigned by Wagoner in the Hydrology and Floods module talked about this concept specifically, and it was covered on quizzes and tests. So you should go back and review that. It's a very important assumption in calculating recurrence intervals. When we think about what causes recurrence intervals to change, climate is one thing, and certainly changing climates are affecting recurrence intervals in many of our streams. The other major factor in many watersheds that's resulted in changes to the watershed factors that have affected recurrence intervals is the urbanization of watersheds. So whenever we urbanize a watershed, we're often increasing the amount of impervious surface. Impervious surface would be roofs and cement and asphalt and other things that water cannot infiltrate into. If the water can't infiltrate into it, it can't be absorbed and held by the soil and is more likely to rapidly run off, to get into the stream quickly and cause a flood. So the graph on the left here, figure 1.15 from the PhysRig manual, shows runoff after urbanization, and the dashed line is runoff before urbanization. And what you see is that the lag time before urbanization between the middle of the rainfall and the middle of the flood, the peak of the flood, is longer than after urbanization. This is what we would call we would term this as the watershed has become more flashy. Shorter lag times, higher peaks are more flashy. You'll also notice that the peak of the flood is larger. There might be the same amount of water if we just looked at the sheer number of gallons of water that are discharged during these two floods. In both land use scenarios, we may have the same absolute number of gallons of water discharged from the stream. So in other words, the area under these two curves would be the same. But because of urbanization and the change in the land use, more of that water gets into the stream faster, which makes the peak of the flood higher, and then the rising limb is steeper and the descending limb is steeper. So the water gets in and out of the stream system faster, causing these flash floods. The diagram on the left shows the same thing with a picture of an agricultural watershed and an urban watershed, and another illustration of the difference in both magnitude, or the peak of the flood, and the lag time of the flood. Now, some good examples of how recurrence intervals and probabilities of occurrences have changed in some watersheds. In a document called the 100-Year Flood that the USGS put out about 20 years ago or so, they compared changes over time in flood magnitudes in these two watersheds. On the left is Mercer Creek, which is near Bellevue, Washington. What you can see is that the area of the graph from about 1950 to 1978 or so is it's shaded blue, and the peak discharge for any given year in that time period was right around 400 cubic feet per second. And the minimum was just under 200 cubic feet per second. So we had a range of about 200 cubic feet per second from the lowest peak discharge for any given year to the highest peak discharge. And from those data, they had calculated that the 1 in 100 year flood was roughly that 400 cubic feet per second discharge. Then Bellevue experienced a rapid urban development starting in about 1977 or 1978. And after that period, as the amount of impervious surface rapidly increased, you see that the nature of the annual floods really changed. Very few years after 1978 have a peak discharge that's actually less than that maximum peak discharge for the earlier period of 400 cubic feet per second. What you can see here is that almost all of these discharges post 1978 are greater than what used to be the biggest discharge ever recorded. There are a few that are smaller, but we also see a much bigger range. We have a little over 800 cubic feet per second all the way down to just below 200. So we went from a range of about 200 cubic feet per second highest flow to lowest flow years to over 600 cubic feet per second variation from our highest to lowest. So we're seeing more discharge, or more big discharge events, and a greater annual range and variation of these discharge events. So that's telltale signs of urbanization in this watershed. Now the Green River near Auburn, Washington, we see something that's very different. Here we have a stream that before about 1960 or the early 1960s had big variations in discharge. We have really dry years, which were down here around 5,000 cubic feet per second, and our biggest discharges, or 100-year flood, was up here around 27 or 28,000 cubic feet per second. Now, so we had a big range. This is not necessarily because this watershed was urbanized. It was just sort of the confluence of watershed factors in this watershed led to this big range in annual flood size. After 1960, we see that there's a big change in the hydrographic response. Now, maybe in the Green River watershed, it just didn't rain as hard after 1960 as it did before 1960. That's possible, but that's not actually what happened here. The Howard Hansen Dam was completed on this river in about 1961, and as a result, that dam is now controlling floods. So when you get a lot of rain and a lot of runoff, the dam holds back that water and then slowly releases it. Similarly, in our driest years, when we have lower peak discharges, the dam lets most of that water go through. So we don't see much change in our minimums, but we see a big change. We've cut the top off our floods by storing that excess water and slowly releasing it over the course of the year, which has flattened out our discharge response. So now, from 1962 to 1994 in this graph, this dashed line, we see that the 100-year flood is a lot smaller. So this is an example of a successful flood mitigation project. Put in a dam to control the flood, and it has really dampened the flashiness and magnitude of the peak floods. Now, one thing I want to note is not all dams are for flood control. Some dams are for other purposes and have no effect on flood control, but this one was specifically designed to control floods on the Green River. Okay, our exceedance probability curves. This is a set of curves that shows for any month of the year for a particular stream. In this case, it's the Yakima River near Parker, Washington. What the maximum probable discharges are for that stream. So if we look here at December, in December, the 90% probability discharge is about 8,500 cubic feet per second, meaning that there's a 90% chance that the maximum discharge in December will be less than 90%. There's a 10% chance that the maximum discharge will be less than about 1,000 cubic feet per second if we look at this bottom lightest shade of pink on this graph for December. So I'm going to pose some questions for you and let you think through them and answer them. You might want to pause the video and make sure you can come up with the right answers. But what's the probability of a 10,000 cubic feet per second discharge in May? What would be the normal discharge in May? So that question's asking, what does normal transfer to or translate to in terms of probabilities? A normal is probably a 50% probability. 50% chance it will occur in any year. That's probably close to your normal discharge. Another question to think about is look at these probability curves and answer the question of how important are summer thunderstorms in terms of causing floods in this stream? Another way to phrase that question would be, what season of the year do we see the highest probabilities of large flows? Okay, so a quick review of recurrence intervals. And for the review, I'm going to ask you some questions and let you think about these. If you're not sure of the answers, you can go back and review what we've talked about in this lecture so far, or you can refer to some of the reading assignments that are out there on Blackboard for this module. First, can a 100-year flood occur 2 years in a row? Express what a 2% probability flood would be in the X year flood terminology. X year is a 100-year flood, a 500-year flood, a 1,000-year flood. What would a 2% probability flood be in that terminology? Based on a statistical analysis of flow data collected from 1905 till 2005 for a hypothetical watershed, it is determined that the 1% probability flood has a discharge of 1,000 cubic meters per second. Since 2005, the watershed has rapidly urbanized. Would you predict that the 1,000 cubic meter per second flood is still the 1% probability flood? If not, would the probability be higher or lower than 1% for a 1,000 cubic meter per second discharge?